Hello dear students. In today's lecture we'll start with another topic, that is event detection. We'll discuss event detection in ECG as well as the EEG signal. So this lecture will be mostly on the events that are in ECG signals and how we can detect, and then the lecture in continuation to this will have event detection in EEG signals. So event detection is an important step in biomedical signal analysis. As we know that biomedical signals carry signatures of physiological events. The part of a signal related to a specific event of interest is often referred to as epoch. Analysis of a signal for monitoring or diagnosis requires the identification of epochs and investigation of the corresponding events. Once an event has been identified, the corresponding waveform may be segmented and analyzed in terms of its amplitude, waveform, wave shape, time duration, intervals between the events, energy distribution, frequency content, and so on. A good understanding of signal events will help in designing appropriate signal processing techniques for their detection. So as we have seen that there are different events in ECG signal. So first we will discuss about the P, QRS and T waves in the ECG signal. If we view the cardiac cycle as a series of events, there are the following epochs in an ECG waveform. We have the P wave. Contraction of the atria is triggered by the sinoatrial node impulse. The atria do not possess any specialized conduction nerves as the ventricles do. As such, contraction of the atrial muscles takes place in a slow squeezing manner, with the excitation stimulus being propagated by the muscle cells themselves. Therefore, the P wave is a slow waveform with a duration of about 80 milliseconds. The P wave amplitude is much smaller, around 0.1 to zero point 0.2 millivolt, than that of the QRS because the atria are smaller than the ventricles. The P wave is the epoch related to the event of atrial contraction. And we should know that atrial relaxation does not produce any distinct waveform in the ECG as it is overshadowed by the following QRS wave. Now next is the PQ segment. The atrioventricular node, that is AV node, provides a delay to facilitate completion of atrial contraction and transfer of blood to the ventricles before the ventricular contraction is initiated. These things already we have discussed when we were discussing about different parameters in the ECG waveform. So this is just a kind of brief review again. So the resulting PQ segment of about 80 millisecond duration is thus a non-event. However, it is important in recognizing the baseline as the interval is almost always isoelectric. Now the next is QRS wave. The specialized system of Purkinje fibers stimulate contraction of ventricular muscles in a rapid sequence from the apex upwards. The almost simultaneous contraction of the entire ventricular musculature results in a sharp and tall QRS complex of about 1 millivolt amplitude and 80 to 100 millisecond duration. The event of this ventricular contraction is thus represented by the QRS EPO. Then we have the ST segment. The normally flat, again we can say the isoelectric ST segment is related to the plateau in the action potential of about left ventricular muscle cells. The duration of the plateau in the action potential is about 200 milliseconds. The ST segment duration is about 100 to 120 milliseconds. As in the case of the PQ segment, the ST segment may also be termed as a non-event. However, myocardial ischemia or infarction could change the action potentials of a portion of the left ventricular musculature and cause the ST segment to be depressed or elevated. The PQ segment serves as a useful reference when the isoelectric nature of the ST segment needs to be verified. Next is the T wave. The T wave appears in a normal ECG signal as a discrete wave separated from the QRS by an isoelectric ST segment. However, it relates to the last phase of the action potential of ventricular muscle cells when the potential returns from the plateau of the depolarized state to the resting potential through the process of repolarization. The T wave is commonly referred to as the wave corresponding to ventricular relaxation. While this is indeed correct, it should be noted that relaxation through repolarization is but the final phase of contraction. So contraction and relaxation are indicated by the upstroke and downstroke of the same action potential. Therefore, the T wave may be said to relate to a non-specific event. The T wave is elusive, being low in amplitude of around 0.1 to zero point 0.3 millivolts and being a slow wave extending over 120 to 160 milliseconds. It is almost absent in many ECG recordings. Rather than attempt to detect the often obscure T wave, one may extract a segment of the ECG that is 80 to 360 milliseconds from the beginning of QRS and use it to represent the ST segment and the T wave. Now let's discuss how we can detect the various events. In that, first we will discuss a simple method for the detection of QRS wave, that is derivative based methods. So this is mainly used to remove low frequency artifacts, as we know that QRS complexes are mainly they possess high frequency components. And it also removes the part of the input that are constant, because we know the derivative of a constant is zero. And also the large changes in input, it will produce high values in the output, so as for QRS complexes. Now the simplest form of a derivative based operator, as you can see in equation number 1, it is given as yn is equal to 1 by t xn minus x of n minus 1. So how we can obtain the transfer function? We can obtain the corresponding transfer function for this by changing it to z domain and then computing yz by xz, that is nothing but hz. So it will come equal to 1 by t 1 minus z inverse. And to obtain the frequency response, that is h omega, we have to substitute z as e raised to power j omega t. So you will get, and also we can keep t as equal to 1. So you will obtain the frequency response as you can see in equation number 3, that is 1 by t e raised to power minus j omega by 2 into 2 iota sine omega by 2. So you'll get the magnitude, that is 2 by t mod of sine omega by 2, and phase, that is pi by 2 minus omega by 2. So you can see in this figure also, this is a magnitude response and phase response. So phase is a kind of linear, it is having a linear phase, and if you see the magnitude, so these low frequencies are getting suppressed, so it can be used as a, we can say, high pass filter, which is removing the low frequencies. Now let's have another operator, that is 3-point central difference operator. Now improvement over derivative based operator we can do by taking average of two successive output values. So you can see in equation number 4, it is average of yn plus y of n minus 1, that is the two successive output values. And if we keep the values of yn and y of n minus 1 in terms of input, so you'll get finally the equation number 5, that is 1 by 2t xn minus x of n minus 2. So how we can obtain the transfer function, that is again by changing this into z domain, taking the reciprocal, so it will give yz by xz, that is nothing but hz, so it will be 1 by t, 1 minus z inverse into 1 by 2, 1 plus z inverse. So if you see this equation number 6, you can see that it is a cascade of two separate filters. One you can see is a derivative based approach and other is nothing but a 2-point, you can say, a moving average filter with the tap weights being 1 by 2. So this can be a band pass type of filter with zeros at z equal to 1 and minus 1. The transfer function, as I mentioned, of this 3-point central difference operator are the two filters in series, or we can say the cascade. One is the first order difference operator and other is a 2-point moving average filter. Now you can see the magnitude and phase response. So it is a kind of band pass filter and also it is having a linear phase. So it will suppress the very low and very high components and it will pass the frequencies in the corresponding band. Now let's see how this derivative based approach can be used for QRS detection. So QRS complex has the largest slope, that is the rate of change of voltage in a cardiac cycle as a means of rapid conduction and depolarization characteristics of the ventricles. So this derivative operator is the logical choice to detect the QRS complexes. Also, derivative or gradient operator boost the high frequency signal. So, and also it is sensitive to noise. So this is a simple block diagram which shows a application of derivative based approach to obtain the QRS peaks. So in this, ECG signal is passed through a derivative operator followed by a thresholding device. The function of this derivative operator is to suppress the other part of the signal and boost the QRS complexes. Thresholding will help in detecting the peaks of QRS complexes. So this technique is proposed by Balda et al. And this technique is further studied and improved by Hellstrom and Tompkins, Friesen et al. So you can see another block diagram. Now what is a change in this? We have added one filter. So that filter is mainly to suppress the high frequency noise, if any is there. So derivative operator is to suppress the other part of the signal and boost the QRS complex. Thresholding is there to detect the peaks of the QRS complexes. So 3-point first derivative of the signal, as we have seen the transfer function already. So you can see here y naught n, which is mod of xn minus x of n minus 2, and the second derivative of is approximated as, you can see, y1n, that is mod of xn minus twice of x of n minus 2 plus x of n minus 4. So when we take the weighted combination by keeping, you can see, 1.3 as one weight and 1.1 as the other weight, so that is a researched values. So 1.3 times of 3 point first derivative and 1.1 times of the second derivative. So that will give us a weighted combination. And this result y2n is scanned with a threshold of 1, and the subsequent 8 samples are tested against the same threshold, that is 1. If at least 6 points pass this threshold test, the segment of 8 samples is taken to be a part of QRS complex. So this procedure results in a pulse with its width proportional to that of the QRS complex. Now you can see in this figure, the topmost trace represents 2 cycles of a filtered version of the ECG signal. You can see here we have uh, two, this you can see we have 1 and 2 cycles of a, we are assuming, a filtered version of any ECG signal. This signal was filtered with an 8th order Butterworth low pass filter with cutoff frequency 90 Hz, and it is again downsampled by a factor of 5 and then filtered with a notch filter of frequency 60 Hz, mainly to reduce we can say, the noise as well as the power line interference. Then this signal was normalized by dividing its maximum value. Then second and third plot, if you see, they should represent the first order derivative and the second order derivative respectively. And y2n, means fourth plot, will represent the combined, or we can say weighted combination of y0 and y1. So we can observe the relatively high values in the derivative based results of the QRS location. The outputs are low or negligible at the P and T wave location, in spite of the fact that the original signal possesses an unusually sharp and tall T wave. Also, if we see the Y2N, that is this, if you see this, it has multiple peaks over the duration of QRS wave due to the fact that the QRS complex includes 3 major swings, that is Q2R, R2S and S to ST baseline in this example. So this last plot, basically it shows the smooth result. We have applied smoothing to obtain Y3N by passing Y2N through a moving average, that is MA filter, as computed by using simply this equation, that Y3N is equal to 1 by 8 summation k running from 0 to 7 Y2N minus k. So this is a moving average filter which take the combination of 8 respective output samples. We then have a single pulse, if you see in this diagram Y3, with amplitude greater than 1 over the duration of corresponding, you can see this greater than 1, so this part, duration of the corresponding QRS complex. So a single peak searching algorithm may be used to detect each ECG beat. The net delay introduced by the filter should be subtracted from the detected peak location in order to obtain the corresponding QRS location. Now we can note here the peak searching cannot be performed directly on an ECG signal, as the QRS might not always be the highest wave in the cardiac cycle, and also the artifacts may easily upset the search procedure. Also, the ECG signal in this present illustration was filtered to restricted bandwidth of 90 Hz before the derivatives were computed, and that is, it is free of baseline drift. Now, next event is dicrotic notch in the carotid pulse. The closure of the aortic valve causes a sudden drop in aortic pressure that is already on a downward slope at the end of ventricular systole. The dicrotic notch inscribed in the carotid pulse is a delayed upstream manifestation of the insera in the aortic pressure wave. The dicrotic notch in a specific signature on the relatively nondescript carotid pulse signal and may be taken as an echo related to the event of aortic valve closure. The signal event also signifies the end of ventricular systole and ejection as well as the beginning of S2 and diastole. So here is the problem is to detect the dicrotic notch in the carotid pulse signal. Lehner and Rangayan proposed a method for detection of dicrotic notch that used the least square estimate of the second derivative, that is Pn, of the carotid pulse signal Yn, which can be defined, you can see in equation. So Pn is equal to 2 times y of n minus 2 minus y of n minus 1 minus 2 times yn minus y of n plus 1 and plus 2yn plus 2. So if you see it has y of n plus 2 terms, so this expression is mainly non-causal. So it may be used or it may be made causal by adding a delay of 2 samples. So the second derivative was used to the fact that dicrotic notch appears as a short wave riding on the downward slope of the carotid pulse signal. A first derivative operation would give an almost constant output for the downward slope. The second derivative operation removes the effect of downward slope and enhances the notch itself. So the result was squared and smooth again to obtain, as you can see in equation this, Sn summation k running from 1 to capital M p square n minus k plus 1 into wk, where wk is a linear weighting function which is given as m minus k plus 1, and we are assuming for the time m equal to 16 and the sampling, that is fs, is 256 Hz. So this method yields 2 peaks for each period of the carotid pulse signal. The first peak that represents the onset of the carotid upstroke, and the second peak that appears in the result within a cardiac cycle is due to the dicrotic notch. So to locate the dicrotic notch, the local minimum in the carotid pulse within a plus minus 20 millisecond interval of the second peak needs to be located. So you can see in this diagram, this upper figure illustrates 2 cycles of a carotid pulse signal, and this signal was low pass filtered at 100 Hz and then sampled at 250 Hz. The result of application of the method just we have discussed, that was produced by Lehner and Rangayan, is shown in the lower plot. So we can see that the second derivative has successfully S into this, you can see that S intuated the dicrotic notch. A simple peak searching algorithm may be used to detect the first and second peaks in the result. So the dicrotic notch may then be located by searching for the minimum in the carotid pulse signal within a plus minus 20 millisecond interval around the second peak location. So this was all in this lecture. Now, in next lecture, we will discuss about the events which are present in the EEG signal, and we'll see how we can detect some of those. So for now,